Welcome to this Mechatronics lecture recording where we'll be discussing control. So up to now we have built all the building blocks to develop a electrical and mechanical system that can interact with one another. We know how to control the actuators using typical electronic circuits, for example like an H-bridge or MOSFETs, in order to actuate a DC motor, brushless DC motor, whatever it might be. We also have developed the information to sample all the data, making sure we don't have aliasing of the signal, adding some filtering if needs be. And now we get to the point where everything is in the digital domain and we need to sample a desired output that we want to obtain, sample the actual output, and then use some sort of controller to dictate to our system what should happen to the actuators in order to achieve the system. So none of this should be new to you. By now, everyone should be familiar with control systems, which is done in MBB in the 4th year. In this lecture, however, we're going to go through control in a much more practical manner. We will develop basically a PID controller, or implement a PID controller and fuzzy logic controller, look at some of the practical aspects there. The actual design coefficients used for the PID, that is something that you can look at in MBB to tune the controller. We will just see how we can implement it in an actual environment. The PID controller, or proportional integral derivative controller, is one of the most widely used controllers in industry. While if you go look up modern controllers in literature today, you'll typically find controllers such as model predictive control, non-linear model predictive control, LQR controllers, or sliding mode controllers, or variants of these controllers. However, these controllers are typically used to solve nonlinear problems in very complex systems, which is generally where literature is trying to improve the controlling of these complex systems. However, in industry, you'll still find the PID controller or variants of it used in industry as one of the most widely used controllers. And this is because it's very easy to implement and generally very easy to tune, either using manual approach by simply tuning the values and seeing what happens, and from there you can sort of see what the controller gain should go to, or from the methodologies developed in MBB, where you can actually firstly develop a model of the system and from there actually develop your controller design. So the proportional integral derivative, or PID controller, starts off by firstly determining an error term. Now the error term is nothing but the difference between a set point or our desired output. So if we're just doing some pressure vessel controller where we want to set the pressure inside a vessel, then we will have the set point as, say, 10 bar, that's the internal pressure we want. Or if you're doing a speed controller, cruise controller, we might want to say we want to drive at 120 kilometers an hour and therefore set the desired output to this value. And then we actually measure the output using some sort of sensor. And for example, again, in the pressure control, we would measure the pressure using a pressure sensor. And in the cruise control, we can either measure it using wheel speed sensors or GPS. However, wheel speed sensors is something that will still work when you're underneath in a tunnel where there's no GPS reception. So that's generally the norm to use wheel speed sensors. So we have a set point and a measured quantity, and the difference between this is termed as the error. And then using this error, we can get the individual terms of the PID controller, the proportional integral derivative controller, and then the total output is simply the summation of those three. So in continuous space, the controller output is written as this, where we have the proportional term, which is simply the error term, which we've already calculated now, multiplied by some gain. And again, this gain is a positive quantity, which generally is tuned or developed using some theory. And this is part of the tuning to get the desired output or desired response of the system. And then we have the integral term, where we have the error term which we integrate over time. So we accumulate all the errors over time. So if the error is continuously positive and there, this term will increase and increase and increase and increase until the error term eventually drops down to 0. And again, we multiply it by a gain Ki, which again is something we develop through theory or tune it manually. And then we have the derivative term, right, where we take the derivative of the error and multiply it by a gain as well. And this term typically improves the transient response of a system. However, I'll give you some caveats, which in general in practice, you should be careful when implementing in a derivative controller, or the derivative term. Now, the PID controller is generally the total controller. We can sometimes only have a proportional controller, so therefore we have Ki and Kd equals to 0. Or we have a PI controller, where again the derivative term is 0, or a PD controller where the integral term is 0. Quite often the most common cases would be having a proportional controller or a PI controller, and then having a PID controller. Very seldom would you get something that's just a PD controller in essence. In MBB, you'll note that again the integral term is basically adding a pole at the 0 of an open loop system. So typically when we have a type 1 system, by having the integral term, we will have a 0 error state in our output. Again, you can go back to MBB to get the detail of this. And the derivative term adds a 0 to our system, which generally improves the transient response of our system. So this is the continuous case where in MBB you typically design according to continuous space. There is a transform, you can go from continuous to discrete space, called the Z transform. But for now, we're simply going to look at how can we implement these terms in a discrete form, not necessarily how to tune or develop the actual controller terms, just to implement it at this point in time. So the proportional term is again very straightforward, whether it be derivative or integral. We simply have an error term and we multiply it by a gain. For the integral term, instead of having continuous integration, we discretize it. We simply say it's the sum of all error terms times delta t. So again, this term increases as time progresses. So in general, you will have a initial error term. So we'll have, say, integral error term, which will initially we'll say 0, and then we'll say integral term is equals to the previous integral term plus e times delta t. So again, this would again accumulate errors, and this term would generally increase if the error term is positive. And then the derivative term is simply done by using finite differences. We take the previous error term and store it, subtract that from the current error, and we have the difference in errors. So, and then we divide it by delta t. And again, this delta t is the time between the controller steps. So again, this controller would run at, say, 1000 Hertz. So if we're sampling our analog data perhaps at 1000 Hertz, our controller might run at the same frequency. Or you might want to sample your analog data much faster, say 10 or 100 kilohertz, and then do some averaging, some filtering using that data, and then run your controller only at 1000 Hertz. Again, really the controller should be running at a frequency that is at least typically 10 times the bandwidth that of the system you're controlling. So if your dynamics of your system is 1 Hertz, then you need to at least control and run your system at 10 Hertz. That's the sort of minimum, generally, rule of thumb that you can use. Okay, so once we've determined all of these terms, we have an integral error, we have a derivative error, we simply multiply them with our 3 different gains or coefficients, and then the summation of these is our output. And again, the output can be anything. So for example, if we're doing a speed controller of a motor, the output would be the voltage supplied to that motor, or the PWM which supplies to that motor. And again, generally the output of the controller can be any form. If you're developing it, if you're manually tuning it, if you're developing it in MBB, we solve sort of a plant of a system. Again, there depending on how you model your equations, whatever the output of the controller is, could be again in the terms of volts or duty cycle, whatever. For example, again, if you have this speed controller of a DC motor where the voltage is between 0 and 12 volts that we're supplying to it, and again, depending on what the voltage is, we'll get different speed out. The Duty cycle, we typically get a different voltage by applying a duty cycle to our PWM signal, which is applied to our H bridge that does the speed control. And the output of our controller can be either duty cycle or the actual voltage. And the difference would be that, again, since our PID typically assumes a linear system, you can have the same controller design with either duty cycle or the voltage output. The only difference would be your gains will be slightly different because you're now accommodating. It's basically like having an additional gain in the system. For example, again, say if we have an output which is maybe easier for now for 0 to 10 volts of our DC motor, but we have a duty cycle which is between 0 and 100%, then note we might have, if we're running on this system, we might have gains which are 10 times smaller than if we're running a system which the output is here. Okay, so just for example, say a PID controller doesn't really care what the output is, as long as your gains are suitably chosen that the output or the system is stable, we get the response that you want. So all you need to do is determine the error and then tune the gains and have the output now supplied to whatever it needs to be supplied to in your actuator. Should you add control, should the voltage over a system increase, should the current through a system increase, or so forth, that's dictated by the output of a system. So for example, again, here is an example we can have. Say we want to have a position control of a DC motor, and we want the desired angle to be 90 degrees. So again, here we can have that the error term is 90 degrees, or if you want, you can again use the error term in radians. Again, the difference is simply going to be your gains are going to be slightly different in essence. And now we can measure the actual error angle by using an encoder or a pot or whatever we find that we want to use. And this is again, if we now say we want to do our control at 100 Hertz, we will find that delta t is 0.01. So our integral term again can be written as such. We initialize it by saying EI is equals to 0, and then this is shorthand notation by saying EI is equals to EI plus E delta t. So that sort of shorthand, it sort of replaces this term and just writes it as plus equals to. So that is our integral term. And again, we have our derivative term where we save the previous error value, and then we work out the differential error, and then from there we can apply our controller. Now, important to note, and we'll discuss this a little bit later, is the problem with adding derivative control to your system is that in a simulation environment, you'll typically always have very clean signals unless you add artificial noise to your system. But in general, simulations are perfect. There's no noise. Everything is clean. So the derivative is typically going to be very smooth and continuous. However, when you are working in a practical environment, the measurement of the system is using some sort of sensor where again noise can be introduced by the environment or by vibrations in the system, which is not in essence noise, but it's not something we want to necessarily take into consideration. Or again, magnetic fields or whatever it might be, so we will get some noise in our measurement, and therefore we might need to differentiate our error term. And again, this will be, I'll show you some indications of why this is very important later. So a very easy approach to filter our derivative term is to use a first order equation of our differential error, where we now have a filtered differential error. And again, now what we have here is the previous filtered differential error multiplied by 1 minus alpha, and alpha again is a parameter between 0 and 1, which we'll get to now, plus alpha times the actual error, the noisy error, which we will see now. And again, this alpha value is basically the amount of filtering to apply. So for instance, if alpha is effectively 1, then this term will fall down to 0, and our output of our system will be our filter output will be the same as the input in essence, so there's no filtering performed. As soon as alpha reduces, goes closer to 0, then we have increased amount of filtering, because now the error term is closer to the previous error term, and we only add a slight bit of the actual error. What this does, however, again, this is basically, again, a first order system where we have a time constant, is that instead of an error, which if we assume we have a clean error, instead of having an output like that looks like that, we will have an output which looks something like this. And again, we will have at 63%, we will have tau, which is the time constant of our filter. So now what we can do is we can actually develop our alpha value based on the time constant. Here I have the time constant as TF, but that's the same quantity. So based on how much delay of the filtering you want to add, because again, as we said previously in filtering, the more filtering you add, the higher the delay of the signal. So, you know, if we filter the signal at this quantity, we might get a cleaner signal, but still maybe noisy. If we add filtering, we might get a cleaner signal, but a higher delay. And again, there's a compromise between these two. More filtering, which gives a cleaner signal, but a higher delay. At some point, you know, you have to make a compromise. Do you want? Can you handle the additional noise, or is the added delay not too problematic? So there's a compromise between those two quantities. So again, simply by having the sampling time of your controller and the time delay, you can then solve for what is the alpha value in our control output. And then again, the output is simply the summation of all of these terms put together. Another equation of the PID controller is sort of, instead of always having this integral term which you solve or having a previous error term, there is an approach which we basically only have to save the last two error terms, in total 3 error terms, the current error term, which is ET, then ET minus 1 and ET minus 2. So 3 error terms that we have to determine, 2 previous ones and the current one, and then simply saying the current output is equal to the previous output times this update. So this is sort of an update step, which you simply have again the same values, the sort of integral gain, which is now the ratio of Kp over Ki, and the derivative gain, which again is a ratio of Kd over Kp. So all the other terms are known. We simply have to save the previous 3 outputs, as well as the 2 previous errors in the current error term, as well as the previous output, and then you can simply update the output to say the new output is now given as this. So some might want to use this approach. The only disadvantage with this approach is you can't additionally filter the derivative term, because you're only working with the actual error quantity. So if your error term is noisy, this would not necessarily, you won't filter the derivative error term, and therefore you will have a noisy derivative error term, which might affect the result. So as soon as you add the derivative error, the previous approach by separately filtering the derivative error is a much better approach to follow, but this might be in certain instances easier to code for some people. So let's have a look at the different controller terms and what their general effect is on the controller. So again, we're going to look at this from our position angle controller. So now you would note that if you go through the mathematics, that a position controller for a DC motor is a type 0 system, right? So irrespective of what the gain is of P, we will always have an error term of 0, and we can clearly see by the different plots. So we start off by having, in this case, a set point of 90 degrees, and we select Kp as initially 5, and then we increase the value. What we can see is, again, with an error Kp gain of 5, we get a reasonable response that doesn't really overshoot, but the sort of time constant, which will probably be around here somewhere, is quite high at over 2 seconds. So as we increase the gain to 10, we can see that the response is better, but now we see some overshoot. So again, by increasing the gain, we see more overshoot. So with a gain of 20, we see a much higher response time. Sorry, roughly over there. So now close to a 1 second response time. But we now also have significant overshoot. We now go to up to just over 110 degrees. And as we increase the gain further, we now see oscillatory nature coming out. Okay, so we start increasing the stability. In this case, not really speeding up the control. I think partly because in this case I put a saturation limit on the controller. In essence, that the voltage output can't go infinitely high. We have to physically cap it. So in this more realistic non-linear sort of system, we have limits of the voltage. Adding additional proportional gain doesn't really improve the stability or improve the transient response, but does definitely give you a more oscillatory nature. So there's a limit in terms of the proportional gain. But again, what we see is more proportional gain, the faster response, but the more overshoot we have in our system. So here is again the proportional gain, but now looking at as a type 1 system. So this is a speed control motor. So again, we're not looking at the angle of the motor, we're now looking at the speed of a motor. And again, if you go through the dynamics, you'll see this is a type 1 controller. And we know from a type 1 controller, as Kp approaches infinity, we will have an error which approaches 0. But we will effectively always have a finite error with a finite value of Kp. And here we can see this. Again, as we increase Kp, we see the error term decreases. However, again, at a very high gain, we see some oscillatory nature popping up in our system. And again, this is not ideal to have. Okay, so again, while we can drive the error out using the simply by increasing the proportional gain, it does mean our stability of a system is slightly affected, or the overshoot and response of a system might be slightly affected by that. So now we're looking at the PI controller on the speed controller. Now again, the idea here is that we basically add a pole at the origin, and this converts the system to a type 1 system, where we will now have an error of 0 if we have a PI controller effectively. So again, with the previous slide, we saw that as we increase the gain Kp, we basically reduce the error, but we could never have a 0 error term until Kp effectively approaches 0, infinity. So in this case, by simply adding a integral term, we can see that the error approaches 0 irrespective of the Kp value. Right, so you can have a very low Kp value, the error will eventually go down to 0. It just might take a long amount of time. So what I simply have here is the same sort of proportional gain, and simply changing the integral term. And what we can see is that the rates of sort of the error reducing increases the higher the gain is of the integral term up to a point. So again, we have a Ki of 20. We see that it takes a while for it to go down to a error of 0. And as soon as we increase that error, increase the gain, we see that the error is reduced much faster in essence. But now, as soon as we increase the integral term gain, we can see more oscillatory nature, a higher sort of overshoot of our system. And in general, the reason for this is because only when the graph goes through 0 do we have a 0 error value, and therefore we're not increasing the error term. So this whole phase from here downwards, the error term is positive all the time because we have an output of 10 and the actual measure value is lower than that. So we have a positive error term and it accumulates error. So by the time we get to here, that does not necessarily mean the integral term is 0. That means we've accumulated a lot of errors up to this point. This is the first time we're not actually increasing or decreasing the error term. So we overshoot, right? And this is now where the error term is negative. And now the integral term is reduced, right? Until eventually we have, and if the gain is very high, we now will have sort of, again, the error term decreasing too much until it becomes 0, and we have this slightly oscillatory nature until eventually it settles down. So that's a problem with having too much integral error. An integral error term will always generally introduce oscillations in your system, right, or increase the overshoot of your system. So if you have a P controller and you add, and it has some overshoot by adding integral term, you typically always will have overshoot, an additional overshoot. There are ways you can circumvent it with sort of additional added complexities to the PID controller. For example, you can switch on the integral term after a certain point. So in the startup phase, the integral error is 0, which reduces what we call wind up, and only at a certain point you switch it on. But again, that is much more complicated to do. So here we basically now have a full PID controller. In essence, again, what we can see is if we have sort of the best solution we could find for our PI controller is the blue curve over here, which shows a very quick response but some overshoot and a steady state error of 0. Now we add the derivative term and we get this orange curve where we can see the response time is still very quick. We get almost exactly the same response time. However, the overshoot is significantly reduced and we get a much better response of our system. And again, if we now increase the derivative term, again we can see that it now becomes a much slower response of our system. So again, there is some sort of compromise between having a much higher gain for each of these systems. In general, if one tunes a controller manually, what one can typically do is, if you know that your system that you need to add an additional pole to your system to go from a type 0 to a type 1 system, in essence to reduce the steady state error to 0, then you add an integral term. So if you're doing position control, where again it's a type 0 system, you don't have to add an additional pole to create a type 1 system to get the error down to 0. In that instance, you don't have to add an integral term. The integral term is just going to give you more additional overshoot and slow down the response, whereas if you have a steady state error which is not 0, that's when you want to add integral term. So you don't always have the integral term, you only have the integral term when you have a steady state error which is not 0 with a proportional controller. So you always start off with a proportional controller, see how it typically responds. You can increase the proportional controller to get a faster responding system until it starts to oscillate, or starts to sort of become now very overshooty and maybe oscillate. What you can then typically do is then start adding derivative control, because the derivative control will sort of reduce the oscillations until basically again you get a good responding system. And if you get to that, you can maybe increase the proportional term again and start sort of increasing both of them until you get a system which now starts to again have too high oscillations in essence. At some point you might get a nice sweet spot where the system responds fast enough but does not have any overshoot. Right, and again, if you have a steady state error, only then will you steady state error which is not 0, only then will you add an integral term to your controller. Now, previously I said that we should be very careful when having a derivative term when in an actual system, because the derivative action actually adds noise, quite a high amount of output noise to our controller. So here I basically give an example again. This is now using only a PI controller to show you sort of the noise of our system. So the green line is the actual velocity, but we're now measuring it with a sensor, and the blue curve is our measured system, and we can see that the measurement is actually quite noisy. Now remember that when we determine the derivative, we actually determine the derivative using the last two error terms. So again, if we have a nice curve which looks like that, again we will have a our current error which is perhaps this point, and our previous error which is that point, and we can determine the error. And the next time we work out the error term is this, and again we will have a gradient which looks like that. So if our output is quite smooth, or our measurement is quite smooth, then we'll get a fairly nice smooth derivative. However, what you typically get in practice is, if we, instead of drawing a straight line for ideal smooth case, for a noisy system, what you typically will have is perhaps something that looks like that. So you'll have a derivative error which goes through those 2 points, then a derivative error which goes through those 2 points, and here, and so forth. Right, so you'll see your derivative error here is negative, and then positive, negative, positive. So it's quite a noisy error in general because we're only using 2 terms to approximate the error term. There are approaches where again you can filter the error or the first by having using more points, or you can work out the derivative using more points. That typically smooths it as well. So again, in any sort of system where you have noise on your measurements, adding derivative control typically have a much more noisier output simply because the derivative is noisy. This is sort of highlighted over here. So I've taken the exact same controller, just added a derivative control, and again we can see that now the system, where the system responded previously with our PI controller something like this, we now have a much noisier response. Our output is quite bad, and we can see the voltage we supply to the motor basically goes between our maximum -24 and 24 volts. And again, this is only really due to the integral term, the derivative term, which because we're differentiating, sort of amplifies the noise in our sensor, and we get a very noisy derivative term. And as soon as we have any sort of gain, we basically now have a noisy output. So again, the approach to this is to actually filter the term, which we'll be doing on the next slide. So again, the approach we're going to use to filter the derivative term is to have a filter term, save the previous filter term, and then we have this alpha, which again is a value between 0 and 1, and we simply now have our actual calculated derivative using finite differences. And by simply tuning TF, because again delta T is dependent on how fast you're sampling or how fast the control works, and by simply changing TF, which again is the time constant, which gives you an indication of how long the signal will be delayed by, we can now filter our signals. Again, here I have a clean signal and a noisy signal. So the noisy signal doesn't look very noisy actually when you look at it. It's actually fairly a clean signal. But on the right hand side, the blue curve, so it looks like a backdrop which is blue, is actually the unfiltered derivative term. So it basically goes down, you can basically see it just goes up and down to our maximum, and it's completely noisy and absolutely useless. As soon as we try and use it, you clearly cannot see any sort of trend line on the system. The red curve I show over here, this is the actual error term, determined from the clean signal. And now we can add different filters. So if we have a filter time constant of 0.02, so we delay our signal by 20 milliseconds, then we see the orange curve. So now we can see we get the right trend out. The trend looks correct. The noise is still there, or there's still a little bit of noise left, but at least now we can see some trend, whereas the blue curve is, I mean, again, there's nothing there. It's just absolutely noise. And if we now have a time constant of 0.2, we get the green curve where the noise is now much more reduced, but we can now clearly see a much higher delay between the actual clean signal and our filtered signal. Whereas with the time constant of 20 milliseconds, it's still noisy, but it's very difficult. You can't clearly see any delay between the two signals in essence. So again, yeah, this is the compromise you have to go. Do you want more filtering? Do you want to reduce the error term or the noise on the error term? Or do you want to add more, or by filtering you'll add more delay? At some point, having an error term which is delayed by a couple of seconds, again, does not going to add anything to your controller. So again, the amount of filtering you can add is really dependent on the dynamics of the system. If your dynamics is very fast, then again you can't filter too much because you can't slow down the derivative term too much. If your system is very slow, then generally you can do quite a lot of filtering before any delay would sort of affect the response of your system. So by adding the filtering of our system, or into our derivative term, we now get the actual response shown as here. So now the response is again much better, right? And you can compare this to the PI controller, where again the our voltage output is again still a bit noisy, and this could again be due to the proportional term or the derivative term. Again, if you look at the noise, the output of our PI controller, you'll see a similar sort of noise level. So the derivative term didn't add a lot of noise to it now. But again, instead of having a response which looked something like that, we now at least have a much faster responding system for our derivative term. So again, whenever in practice, when you have to add a derivative term, be careful note that simply by differentiating, you might add additional noise to the output of a system. So be careful when you start adding. At least plot the error, the derivative error, to see whether there's quite a lot of noise on it before simply just using it. So how do we tune the PID? Again, there's manual approaches. You can simply tune the controller and see the response, and from the response you would have an indication of what should be done to the controller gains. Generally a very competent controller designer can do this by simply looking at the response and dictating what should happen to the gains. The advantage of this is obviously you don't have to develop a control system or a plant. You don't have to model the whole plant of the system to develop the controller. There are other techniques as well which can use the actual experimental setup to design the controllers, and some of these techniques which can be used either using experimental setup or by using tuning methods in Laplace domain is the Ziegler-Nichols, Turius-Loewen, Cohen-Kuhn, Åström-Haglund, or using an optimization approach where you basically just iteratively change the gains using a gradient-based optimizer until you get the desired output response that you want, in essence. Okay, but again, in this module, we don't really care much about the how to tune it. If you require to do some tuning of a controller, it'll generally be quite simplistic in nature. You don't have to do a lot of effort to, in essence, get the desired output to be within the desired spec that I specify. Another controller design which has sort of been developed in the last couple of decades is the fuzzy logic controller. Now, the fuzzy logic controller works completely differently to the PID controller, where the PID controller is typically a more sort of analytically based controller design, whereas the fuzzy logic works sort of based on what we call sort of rule sets, in essence. So one sort of basic fuzzy logic controller would be if we want to control the temperature of a system, and we have a fan which blows on the system. So again, the more the fan spins, the higher airflow we have over our component, the faster it cools down. So the higher the temperature, typically the faster the fan should rotate, and the cooler the system, the slower the fan has to rotate in order to cool the object down. So one basic idea would be to have to write this as a sort of word problem. That's again what the fuzzy logic controller basically does, is it breaks down the system in terms of rule sets which can be logically based in terms of what you intrinsically believe should be the best approach, or the outcome should be. So for example, if we're measuring again an object, we want to cool it down. If we're saying that the temperature of this object is very hot, then we should set the fan speed too fast. Else, if the temperature is not very hot but it is still quite hot, then the fan speed should be medium. Right? Or else if the temperature is cool, right, then we might want to set the fan speed to a low speed. If the temperature is cold, then we want to put it really slow. Else, meaning it's very cold, then typically the fan speed should be equal to stop. So this is sort of logically, the hotter the component gets, the faster the fan should speed. Now the question is, what do we find as very hot? So again, the temperature would be a quantity which we measure in degrees, so say 70 degrees, 80 degrees, 90 degrees, whatever we're measuring. And the very hot again is going to be a temperature measurement which will be different values, and it's part of the design logic now to specify what is hot, what do we define as hot, what do we define as very hot and cool, and that's far, and then also what do we define as fast, medium, slow, and so forth. So that's the sort of basic rule sets that we have that we can go from. So again, you can see that in a lot of sort of examples, instead of developing a controller from a mathematical point of view, you can more develop the controller from a logical sort of rule set point of view. So here we have a example which we did with the PID controller. Again, it's to set the desired angle of our DC motor to 90 degrees. And what we do here is, again, we base the control of the error term. So we have a set point that we want, which is 90 degrees. And we actually have a measured angle, which we have, and then we have our error term. In this case, we take the absolute error, which is simply the absolute value of the error. And then what we see is if the absolute error is large, and again, what the definition of large is something we'll have to define, then we put the motor voltage to maximum. So in other words, if the motor is very far away from the position it needs to be at, then let's put the motor speed to the maximum speed you can to quickly lower the error term as fast as possible. If the error term then sort of decreases, right, so it's not very large, it's just large now, then the motor voltage goes to high, so we start slowing down the motor. Again, as the error term reduces, we basically say that the motor voltage should go lower and lower and lower. Right, and now again here, if the error term is basically 0, then the motor voltage should be 0 as well. And then we can simply take in consideration the sign. Should we be rotating positive or negative based on the actual sign of the error? Right, so if there is positive, then obviously it means we need a positive voltage to reduce the error. If there is negative, that means we need a reverse polarity to rotate in the other direction to reduce the error as well. And again, the general rule is that large is the sort of increase in large going from 0 in that direction, as well as the motor volt, the output increases the larger the error is. If we implement this on our desired output, again we will see a sort of output response over here. So if the error is quite large, we go to the maximum, which is 24 volts, and as the error goes down, we basically start stepping it down in essence, and then we get a reasonable output of our system. It does overshoot a bit, and we can see that indeed the error does go at some point to negative and then back to positive, so we do have some oscillatory nature in our output. The only problem is that the output is quite blocky, so we don't have a smooth output. We basically go from 24 volts to 20 volts to 15 volts to 10 volts and so forth. You know, we might get better control, smoother control, if we have a much smoother sort of transition between these two. So a way now to smooth the block output of the previous system to a more smoother continuous output is by the means of using fuzzy logic membership functions. So in the previous output, the state was always at a specific logic state. So we either have the speed was always, if we're looking at the fan speed, the temperature was either always cold or cool or nominal or warm or hot. And based on that states, we had an associated speed of the motor or specific output of the system. But instead of now being either cold or cool, we'll now generally say have a membership between these two regimes, and the degree of membership indicates how much of the output is of a specific value. So for argument's sake, here we have that the cold state, which has a membership of 1 and then drops down linearly until we get to the perfectly cool state. So this is where perfectly cool is. At the same time as the cold state decreases, the cool state increases until it reaches a maximum. And then as it decreases, we then have in the next regime, which is nominal, which starts increasing. So anywhere, if we draw anywhere a line on here, the summation of these 2 points will always be 1. So for argument's sake, if the temperature is between cold and cool, then, but it's closer to cold, then for argument's sake we'll have 0.8 membership of cold and 0.2 membership of cool, and so forth. So now we can use this to, instead of going immediately from cold to cool, to gradually go from cold to cool in a much more continuous output way, which I'll show you in the next slide. So here we previously had our output, which was defined as this. So if we're cold, then let's say the fan speed is 10 RPM. If it's cool, it's at 50 RPM. And if it's nominal, 75, and so forth. So again, as the temperature increases, the fan speed increases. But again, this is very distinct states. So the output will jump from 10 to 50 back down to 10 if it fluctuates between those two logic functions. So now what we say is, well, if we have a state which is not, let's say for argument's sake now cold, the temperature associated with cold is 10 degrees, for cool 20 degrees, and then for nominal 30, 40 for warm, and 50 for hot. So if we're lower than 10 degrees, then we are in the cold state, so have that sort of regime. If we're between cold and cool, then we will be, let's assume we'll then go to the cool state, or we can go to the cold state, but we'll either go to the lower or to the higher state of that. And until we get to between these two regimes, we'll then say jump to this one. And as soon as we get to these two regimes, we'll jump to this one, and jump to that one. And as soon as we're higher than that temperature, then we'll have this value. So we always jump between these two states, when we go through a different logic level. But now if we have a temperature of 12, we can do something different. So instead of now saying we are between cold and cool, and therefore the temperature, the output of the system is going to be the output of cold or fully the output of cool, we want to now have a gradually change. So what we can do is, the temperature that we measure is T, so we can firstly work out what is the degree of membership that we have with the cold membership function. So what we then have is the two states we are in between. So we are again over here, and we're therefore in between states T1 and T2, which has associated temperatures 10 and 20. So what we basically do is, on the lower logic membership function, we have the equation which we have T minus T1 over T1 minus T2, and then the next logic state we have minus T minus T1 over T1 minus T2. What you'll see is basically just a negative sign which is there. In essence, if you do not include a negative sign, what you'll find out is a negative over here, and you can just then sort of take the absolute of that, because we can only have a positive absolute membership to a function. So in essence, if we now have 12 in here, we can visually see that 12 is much closer to 10 degrees than it is to 20 degrees. So what we expect to have is a higher membership of cold than a membership of cool. And now if you work this out, 12 minus 10 gives us 2 divided by 10 minus 20 plus 1. I've got the plus to state the plus 1 there. And what we get then is 0.8. And if you work out the membership of cool, we get 0.2. And as we can see, the addition of these two again is equals to 1. Right, so now what we can say is, well, instead of having the output being fully cold or fully cool, let's now say the output is 0.8 of cold, so 80% of cold and 20% of cool. Because we have an 80% membership of cold, we say that the output must be 80% of its output. And of cool, we have a 20% membership, so we'd say the output is 20% of that. So if we look at the respective fan speeds, we said for cold, the fan speed is 10 RPM, and for cool, the RPM is 50. So then what we have is we say 0.8 times 10 plus 0.2 times 50, and what we get out is a value of 3.3. So now you should note now that the output will gradually change as the membership changes from one level to another one, and we'll always get a nice continuous output. And as soon as we move to this regime, then we'll use T2 and T3 in the equations and so forth. And if we have these two, we will use T4 and T5 to calculate the degree of membership. So if we take the exact same logic that we had previously, we're not changing the temperature levels, or we're changing the voltage levels outputs, we just add the degree of membership to the function, we will get now much smoother output as presented in the next slide. So this shows you the output. So previously we had an output which goes something like this. So now we have a much smoother output. So again, generally what we have is the control will be much smoother, and it won't be as sort of jaggedy, which will also result in typically cleaner signals, as we don't have as high the IDT or the VDT signals, which will be generated by the current flow through whatever actuator we're using. So again, that will be decreased, and again the output is generally quite good. And if again tuning this is now slightly different. You can't use analytical equations to typically tune it. You have to now change your membership levels. So instead of saying 10 and 20 degrees, in this case for the absolute error terms, instead of saying the error above 5 or 10 degrees, we can make the error smaller, or the voltage levels output from the different functions a little bit higher or lower to get a lower overshoot or faster response time in essence. So it's a slightly more difficult to tune perhaps, but it's very easy to implement in essence. And the advantage of fuzzy logic is that if you can sort of formulate a solution verbally or logically, then you can implement a control at least. Whereas the PID, typically, if you're trying to formulate it properly using developing the plant of the system and then developing the controller, you firstly have to go through all that aspects of doing the development of the system before you can actually typically implement it, unless you do manual tuning in such a way. So therefore, fuzzy logic is very easy to implement in systems where you don't actually know what the plant necessarily might look like, or it's very complex to model. You can just sort of put on a fuzzy logic controller and you'll get some result out. The output might not necessarily be as good as the PID controller, where the tuning is much more simplistic in essence, but you can get a sort of non-linear control output from the system based on the amount of functions you use and sort of how large the steps in between those functions are and how non-linear those steps are in fact. So this is the conclusion of control, where we look at the PID controller, which is a more sort of analytical approach, which we also develop in control systems in the 4th year, specific ways of implementing PID controllers. And again, specifically note that when you have a derivative term in a PID controller, that filtering of the derivative term in actual systems in practice is important. Of course, in a simulation environment, you will not see the noise in the derivative term. It's generally then good if you have a system to add noise to your simulations to sort of simulate what the derivative term would do if you have a noisy measurement signal. And fuzzy logic, we basically create different logic functions, and ideally we will create membership of those logic functions so we get a much smoother output of our system. And again, the tuning of these controllers are not something we're really going to deal with in this course. If you ever need to do some tuning, the tuning will generally be manually done, simply changing the gains until a respective sort of output is obtained in essence.